Winter time, come on, grab your friends. We'll go to very distant lands. We'll take the dog and then the human. The fun will never end. It's adventure time.
Hello everyone. In this presentation, we will explore how climate change is affecting wheat production in India and what is being done to tackle it. Wheat is not only a staple food, but also a key economic crop. This study aims to identify the main climate challenges such as heat, drought, and erratic rainfall, and examine how India is developing and using climate-resilient wheat varieties to overcome these issues. We will also touch on how these innovations support food security and sustainable agriculture. To start off, climate change is one of the biggest threats to food security in South Asia. In India, agriculture is a major livelihood source, making the country especially vulnerable to climate-related disruptions such as prolonged heat, droughts, and floods. Wheat, which provides 20% of the global calories and one-third of protein, plays a vital role. However, it is a climate-sensitive crop, with studies predicting up to 23% yield loss by 2050. To adapt, India has developed new wheat varieties like DBW187 and PBW872 using advanced tools like marker-assisted selection, gene pyramiding, and adjusted planting schedules. These varieties perform better in heat and drought while supporting broader goals like zero hunger and climate action.
India's wheat farming is under serious pressure from climate change. The biggest problems are terminal heat, drought, and late sowing. Terminal heat hits during the grain feeding stage, which shortens it and reduces both yield and grain quality. Just a 1 to 2 degrees Celsius rise can cut yields by 3 to 5%. Common varieties like HD2967 and PBW343 don't hold up well under stress. They age early, lose chlorophyll, and show weak photosynthesis. Other than that, heat also causes more internal damage like high ROS level and low enzyme activity. Another key issue is genetics. India has over 20,000 wheat accessions, but breeding programs use less than 1%. Repeated use of similar lines lead to genetic uniformity and shared climate risks. Climate stress is already hurting India's wheat belt. In the Indo-Gangetic plains, temperatures have risen up to 1 degree Celsius, causing more terminal heat events. In rain-fed zones like Madhya Pradesh and eastern Uttar Pradesh, drought is more frequent, leading to yield losses of 20 to 30%. Wheat provides about 40% of India's cereal needs, so production drops, push prices up, drain buffer stocks, and increase import reliance. Most wheat is grown by smallholder farmers who often lack resilient seeds, irrigation, or financial support. This leaves them vulnerable to low yields, high costs, and cycle of debt with little room to adapt. The figure shows the impact of heat stress on sensitive wheat varieties and tolerant wheat varieties.
So for the research methods, the field trials are conducted across diverse climates and environment conditions in India. This to evaluate new wheat varieties in both optimal and stressful environments like late sowing for heat stress and limited irrigation to induce drought stress. This to compare new and old cultivars to identify best performance under climate change. Next method is by genetic screening and breeding. By genetic screening and breeding, we can identify specific traits for heat, drought, and other climate change tolerance. It utilizes modern breeding techniques like marker-assisted selection (MAS) to integrate the beneficial traits into the new cultivars. Lastly, for the farmer participatory research, is to gather direct feedback on variety performance and economic viability under real farming conditions. For the next part in the investigation is the data collected. There are agronomic and yield data, stress tolerance data, environmental data, genetic data, socio-economic data, and the tools used to get the data. So for agronomic and yield data, it is gained by the actual grain yield per hectare, plant height, days to maturity, and other growth parameters. For stress tolerance data, it is indicated by the physiological indicators under heat and drought stress. For example, the chlorophyll content and relative water content. The water use efficiency UE data is also measured by monitoring water applied through irrigation and rainfall. For environmental data like temperature, rainfall patterns, and humidity is acquired from local weather stations. For genetic data, the molecular markers are used to characterize the genetic makeups of varieties. And for the socio-economic data, it is collected via farmer surveys to understand perceptions, challenges, and economic benefits that they gain from the new cultivars. Lastly, for the tools used is some basic field equipment, advanced sensors, drones, and laboratory instruments. So for the final part of the investigation is for the data analysis part. It involves descriptive statistics to summarize data in numerical values and uses ANOVA to give a statistically determine the significance of difference in yield or other traits between varieties. The regression and correlation analysis is also done. Stress indices is done by calculating heat sensitivity index HSI or drought sensitivity index DSI to quantify the resilience in new crops. Then there is the genotype and environment interaction analysis, and lastly the economic analysis to evaluate profitability using metrics like benefit to cost ratio. Now moving on the findings. The findings on climate resilient wheat varieties and their development. The most climate resilient crops show resistant climate change characteristics and by abiotic stresses like heat, drought, and disease outbreaks. In table number 1, the wheat varieties that have climate resilient properties and the approach and methods to develop. There are 6 types of cultivars that be found to have resistance to the climate change. And for the figure 1, it is the figure is schematically illustrates the marker assisted recurrent selection MARS as an advanced breeding approach that's vital for developing climate resilient wheat varieties in India. Next, in table 2, this table showcases the valuable data from the ICAR Indian Institute of Wheat and Barley Research IIWBR on the performance of new wheat varieties. It includes average grain yields in unit quintile per hectare under different production conditions, specifically time zone irrigated and timely zone rain-fed. For example, in the variety HPW 349, it yielded 47 quintile per hectare under irrigated conditions and 25.9 quintile per hectare under rain-fed conditions, demonstrating a significant drought stress tolerance. In the next slide, in figure number 4, this figure illustrates gene pyramiding. There is a strategic breeding approach that is crucial for developing climate-resilient wheat in India by stacking multiple stress-tolerant genes into a single variety. It shows the processes of identifying specific genes followed by marker-assisted selection (MAS) over successive breeding cycles, thereby enhancing the wheat's resilience to key abiotic stresses like drought, heat, and salinity. Finally, in table number 3 is the benefit to cost ratio for wheat cultivations in Bihar, which is a region in India. The table highlights the economic advantages of adopting climate-resilient agriculture (CRA) technologies, including resilient varieties. This improved profitability stems from a combination of a higher and more stable use and potentially reduced input costs due to better stress tolerance and less need for pesticides.
India has made real progress in helping wheat crops handle climate stress. One key step is developing heat and drought-tolerant wheat varieties using diverse genetic sources. Farmers are also using early sowing and surface seeding to beat the heat. These methods have shown strong results, especially in hot regions. The figure here shows a surface seeder at work in a paddy residue field in India. This tool can help plant wheat directly after rice harvest, saving both time and fuel. Support from KVKs, seed banks, and agri-universities has helped farmers to get these new varieties. Training programs have also guided farmers on choosing seeds and using water more wisely. With government subsidies, even smallholders can afford these changes. As a result, farmers are seeing more stable yields, better crop health, and stronger incomes even during heat and drought. To build on this progress, we need to get more climate resilient wheat varieties into farmers' hands. This means adding them to national and state seed programs, especially in high-risk zones like the Indo-Gangetic Plains and rain-fed parts of central India. Policies like the seed replacement rate can help speed this up. We also need to keep investing in pre-breeding so future wheat lines can handle even tougher conditions. Next, we should strengthen the seed supply system. This includes expanding community seed banks and KVKs and also supporting public-private partnership for local delivery. Fixing gaps in supply and demand is also a key. That way, farmers always have timely access to the right seeds. Together, these steps can help more farmers grow better wheat even in tough environments. The figure shows wheat heads cultivated from a new climate-resilient seed variety in Karnal, India. Other than that, India must invest more in research and breeding. Programs like the Indian Wheat Genomics Initiative need a better funding to develop wheat that can resist heat, drought, and disease. Support for local breeders and trials with farmers will help turn lab results into a real-world success. Policy support is just as important. We need to encourage sustainable farming methods like early planting, conservation farming, and surface seeding. These can be promoted through subsidies, grants, tax breaks, and crop insurance. By linking research with good policy, we can help more farmers adopt climate-smart practices and protect India's food supply.
To conclude, this case study clearly shows that climate change puts wet farming in India at serious risk. But through smart strategies such as using field trials, farmer input, and modern breeding techniques, India has successfully developed resilient varieties such as DBW187, PBW872, and HPW349. These climate-resilient varieties do not only survive in harsher climates, but also yield better and generate more income for farmers. The findings point to clear steps forward, which are expanding the adoption of climate-resilient varieties, improving seed distribution, boosting research, and strengthening agricultural policies. In short, climate-resilient crops are essential for protecting food systems and ensuring sustainable farming in the face of climate uncertainty. That is all from us. Thank you.